This one. So if you're in, the stuff I covered today is in my last lecture for my master's students in Sheffield. So if you go to my master's course, you'll see a lot of text about Gaussian processes, sampling from the prior, with Python code showing you how to do it, and relating it actually to basis function models, which is the way I introduce basis function models. So for example, here's a really ugly function that is designed for getting people to understand how Gaussian processes work. It computes the kernel function, right? So it's a little bit of Python code that creates a kernel matrix and then computes it, and then you can call that with different covariance functions, and then there's examples for making predictions. All the examples are missing there for you to do in class, but using that basis code about how to play with the Gaussian process. That's not using, we have in Sheffield, we write this software called GPy. So GPy is designed for modeling with Gaussian processes, and it's sort of pip installable. So it's another GitHub repo. So this is BSD license. We have lots of contributors. Loads of people have put into it, and it's BSD, so it's totally free to use, even if you're a company or whatever. And this is a very large framework. So 5,011 commits, 33 contributors. You can fork it. Lots of people are forking it, which is our Gaussian process modeling framework. That's our main software side. So when you use that, you don't worry much about the mechanics. You have to know the mechanics in order to know you're using it correctly. So there's a couple of resources there for things to look at if you want to try these things in practice, and that's the sort of thing you do with the Gaussian process summer school. Okay, so get through this onto the first sort of interpolation example. So Gaussian processes, as I've just described them, now we've got two data points, like before that we fitted with a straight line or whatever, but two data points, and what we want to do is combine them to fit a Gaussian process. But we don't have any noise. And I like this example because you can show that this, if you choose a length scale and a particular scale, so I need to choose two parameters to do this. I have to fix two parameters. One is the length scale of this function, so how quickly it wobbles in this direction, and the other is the overall scale of the function. You can tell that the overall scale is 1 because I'm showing error bars at 2 standard deviations. So as you move away from the data, so as your distance from the data gets large, the function tends to go back to 0 mean and variance 1, which is standard deviation 1, which is 2 standard deviations of 2. So you'll see the error bars move back towards 2 standard deviations. But I've got a point here, and what I'm showing you is the mean of the posterior process as a black line. That's the mean. So this is our mean prediction. Now, be very careful when looking at predictions of this mean. It doesn't really think that there's a weird bump here. This is the average of all the predictions it has. So there is no weird bump. When you look at the posterior prediction of a Gaussian process and you look at the mean function, bear in mind that the mean is often not representative of the underlying function. We'll see some other examples of that later. What you're seeing here is the marginal variance of the posterior, right? So the probability of, at each of these points, the probability distribution here, conditioned on these two. So it's a marginal conditional, if you see what I mean. There's a whole joint distribution over functions that if a particular function that went through here was up here, then the next point would be here, right? It would plot in this certain way here. So the marginal doesn't show you all the information, right, about what these functions look like, which is one reason why Philip does these weird visualizations that you ask more questions about than Gaussian processes. So with these 2 points here, because there's no noise, the function is constrained to go precisely through those points. And the length scale is dictating how quickly the uncertainty blows up as you move away from those points. If I add a third point in, then I get an effect like that. Now, this noiseless prediction is really important in this surrogate modeling domain, this uncertainty quantification. This Antonio Hager, he's like, I don't know, people call people the godfather of things now, so he's the godfather of Gaussian processes or something. he's someone who wrote about them back in the 70s. He's at the University of Sheffield, and Jeremy Oakley, who's still a professor there and an expert in GPs, work on this sort of thing. This might be, the noiseless prediction could be that I've got a large computer simulation of the climate that takes 200 days to run. So I set up the initial parameters of how much carbon we're going to take out and whatever else is going to happen. I run the simulation, 200 days later I get a temperature. These are the parameters, and this is the temperature I get. Right? So this is the temperature I get, but it's a simulation, there's no noise. I want my simulation to reconstruct that. What I want to know is if I've got two other observations, so I then also run my model here and I run my model here. Where do I expect things to be in between? Well, there's uncertainty associated with that, even though there's no noise in the system. There's uncertainty with what the simulation will do. It's a particular type of uncertainty. There's no stochasticity in the system at all, but I'm still uncertain. And this is an area known as surrogate modeling, which is what one of the things we'll focus on in the GPU. So if I add more data points and I'm adding them sort of interspersing the original, I start to get a collapse of the function. I get a collapse of the function around up until this point, when actually it looks really confident about what the function is. Now this, I like to include this because I think you have to be really wary when you see this. What you're seeing here is almost a delta function prediction, because the length scale is such. I can't remember what I actually sampled these points from a Gaussian process, and I'm fitting the same Gaussian process back. So this is sampling points from the model and refitting. The length scale is such that it's incredibly confident about what goes on between the data here. I would be very, very wary if you get to that level of confidence. It's never going to be correct, right? So I like it when I see uncertainty between these points. I don't like this situation. This situation is reminiscent of something that you will come across. Who has got a big background in signal processing? So does this remind you of anything where you collapse down to 100% confidence in a function? Nyquist sampling theorems, band-limited signals. So a band-limited signal in signal processing is one where you say that I know that there's no frequencies above a certain level. So I can say a signal is band-limited at 300 hertz. In that case, I know that if I sample that function at 600 hertz, I will recover that function exactly, if I remember correctly. That's Nyquist sampling theorem. What you've got going on here is something very, very similar. Because it turns out that stationary Gaussian processes have a signal processing interpretation. So this covariance function, the Gaussian covariance function, it's because it's stationary, has an interpretation of applying a filter in Fourier space. So a band-limited filter is one which just goes down the steps like that in Fourier space. There's no frequency above that. If you take the inverse Fourier transform of that filter, that inverse Fourier transform is your covariance function. It's an assumption about function, the stationary function. It's called Vogt's theorem. I'll state it later on more formally. But if you take that band, so who knows what the band, inverse Fourier transform of the step function is? It's the sink, yeah. So actually the sink is a valid covariance function, and it's an appalling one, and you should never use it. Because this assumption that you've got a sort of no frequencies above a certain level is a very, very bad assumption. And it's, again, it's something that people, signal processing, people do this all the time. The algorithm is do Nyquist and then just fit the fit. They forget that the model is, you're saying that there's no frequencies above a certain level, which is not true of any interesting function, right? So the equivalent filter associated with this covariance function is actually the Fourier transform of this covariance function. And this covariance function looks like a Gaussian. So what's the Fourier transform of a Gaussian? It's a Gaussian. Actually, with the length scale flips. So the length scale goes from being on the bottom to the top. So this covariance function is equivalent to applying a sort of Gaussian-like filter in Fourier space to your data. So it has, even though it's not got the same sort of cutoff, let me draw that, right? So the Fourier, the standard signal processing assumption in Fourier space, so this is frequencies you believe in, is that, band limited, and then actually you tend to make it symmetric to avoid complex That's what you believe in, that there's no frequency above 300 hertz. And that leads to a sink, the sink being something really ugly like that. If you invert it, that's the covariance function you get. The Gaussian covariance function, so, and I should say this is as a function of r, where r is equal to the x1, so x minus x prime in the 2 norm, right? So they're functions of the distance between the 2 points. So this is the Gaussian density. It's a Gaussian in R, zero mean, and its Fourier transform is also Gaussian, but with the length scale flip. So if it's very narrow, then the Fourier one will be very wide. So a narrow covariance function is saying, oh, okay, I believe that the function can move very quickly, which leads to a filter that is very wide. High frequencies are present, and vice versa. If we have a narrow filter in Fourier space, then we get a very wide covariance function. Low frequencies aren't present. Note, though, that the Gaussian has support for all frequencies. So in theory, this means it's a universal approximator, right? Because it believes that any frequency can be present. In practice, look what happens very quickly, and this is a bad characteristic of this covariance function. In practice, look what happens is this is not a delta function, actually. This is a Gaussian density with support all along the real line. But its standard deviation is so small that it just thinks it's, it's support, but it's nothing. It's like the probability of any point off this line is 0. Because the Fourier filter is basically saying, okay, those high frequencies don't exist, so it doesn't believe in high frequencies, so it doesn't believe you can oscillate between them. Right? So that's a really nice way of thinking about covariance functions if they're stationary. You can try and map them onto what the equivalent filter would be. Notice, therefore, that that type of signal processing is making Gaussian process assumptions about data. But it's forgetting a little bit what the model is in a probabilistic sense. So remember the model and algorithm thing? So the algorithm I've shown you so far is to compute the whole covariance function, do this matrix inverse, do all this sort of stuff. That's the worst case algorithm. For the Fourier case, you can do things quicker. For those in signal processing, well, no, the whole of signal processing is based around that, and it's very, very fast, right? Signal processing algorithms are going on, there must be thousands between here and my computer, doing all sorts of things with my data, making those assumptions. Okay, questions about that? So that's a fit, but I like to use that fit to introduce this.
After you finish trashing Nyquist, you have to think that this is something from the 30s.
Oh, no, I don't want to trash Nyquist. No, the really interesting thing, if you go back to, I think it's Nyquist, and I learned recently it means new branch in Swedish. Blomqvist means moving branch. Anyway, any Swedes here? Am I right or wrong? Any Swedes? No. Yeah, but go on, what you're pointing about now.
No, the only thing is, it's the thing that you were saying about models and algorithms.
Yeah.
This is a typical model that is thought for an algorithm that is very easy to implement.
Yeah, no, I think
things have to be fast.
The point about the 1930s is vital, actually, because back in the 1930s, people understood all this. Everyone understood all these things. The people that wrote these algorithms, that came up with these theorems, they understood it all. Then they wrote down things that they could do practically at the time, and everyone forgot all the theory and went forward with the practical algorithms. So you've got this massive forgetting of what the people who wrote this stuff down in the first place knew.
Usually in signal processing, assuming that your signal is bandlimited is a good assumption, or it doesn't really matter because you are sampling maybe a lot of information. So do you have an example where it's...
Yeah, almost always it's a bad assumption. So I think usually in signal processing, you're absolutely right. The way that people get around it in signal processing is they say, I'm going to sample a gigahertz because I'm not interested in anything that's going on in the signal. So it's dealt with by computational power. And at the end of the day, these things are so fast that you can do super high rates of sampling. Gigahertz sampling means I'm getting 1 billion points a second. Yeah, which is extraordinary sizes of data, and that's what signal processing how it deals with. If I'm trying to measure what's going on in a time series of my gene expression in one of my cells, so I've got a mouse under development or something, and I want to understand a development issue, I only get to kill 7 mice to cut out the embryos, and each data point is a dead mouse. Or in some other situations, each data point is a dead patient. Or involves a visit to a doctor. So the domains where signal processing will absolutely continue to dominate are those where data is so cheap that you can just do these things. But when you want to start doing, as we'll see an example, quite a high data example for gene expression. Gene expression is just a very complex signal processing system. I mean, it's a load of 10,000 signals. But our ability to sample is massively constrained by the physics of how we sample. So that's one, in those sort of domains, we're number two things. I think Fernando's point is very well made, that within the domain, these are excellent. But once you leave the domain, you actually have to go back to first principles, back to the model, and sort of realize, oh, that algorithm isn't appropriate anymore. I need to look at another algorithm, and I can afford to do a matrix inverse. So we'll see an example of that in a bit. Other questions at that point? Yeah, I shouldn't trash signal processing too much if I was, but I'm just trashing people for not thinking about the separation of model and algorithm, which is really important. Notice another thing: if you are in that domain where you've got a linear time invariant system where you can get the right filter out of it, it's far more efficient to work with that system than it is to explicitly compute the covariance. Simo Saka does a lot of work on mapping covariance functions back into the linear time invariant system because it's much more efficient to do it there. But it's still useful to know what the model is. So far we've talked about the function, observing the function directly. Now the easiest thing we can do is to corrupt that by adding Gaussian noise in the way that sort of Gauss did to get to least squares. Now Gaussian noise becomes equivalent to this form of covariance function. So this form of covariance function is just, this is the Dirac delta, sorry, the Kronecker delta. The Kronecker delta, I always say that, put it wrong way around. Kronecker delta, it says if these two data points are the same index, then add noise. If they're not the same index, they're not correlated. So points are only correlated if they're the same point. That's noise, and it's just the covariance function that we can add in. Now, the beautiful thing about the covariance matrix is if I have one Gaussian distribution, if I have F1 is sampled from a Gaussian, any Gaussian, and then I have F2 sampled from a Gaussian, the resulting variance of the sum is just the sum of the variances. And the mean is the sum of the means. This is another beautiful property. If let's say these were, let's say I do F3, F4, F5, F6, and then I sample these objects from a distribution with finite variance, what would the distribution of this whole thing be roughly distributed as? Depending on the variance and how heavy-tailed those individual distributions. They'll actually be distributed regardless of what the underlying distributions are, as long as they're finite variance. It will be distributed as a Gaussian, because I'm starting to expand the central limit theory. If I take any number of random variables and I add them together, things become distributed as a Gaussian. So for that reason, it won't surprise you to realize that most things, if I add two random variables together, so if I draw these from a student t distribution, as long as it's got a degrees of freedom parameter greater than 2, if I add two random variables drawn from a student t distribution together, they are not drawn from a student t distribution anymore. In fact, they won't be until you add so many of them together that they become drawn from a Gaussian, because a Gaussian is a special case of student t when the degrees of freedom is infinite. So we can add two Gaussian functions together. So if we have functions that from a Gaussian process, two separate functions, one has one covariance function and the other has another covariance function, adding those two functions together gives us a new Gaussian process where its covariance function is just the sum of the originals, which is really beautiful. It's a nice sort of trick. Of course, it's hard to do in Fourier space, right? So this is a trick that works in the time domain for signal processing. It doesn't work in the Fourier domain because adding two covariance functions does not lead to something additive in the Fourier domain. So it's one of those things that works a lot better in the time domain than it does in the Fourier domain, even though it's a reasonable thing you might believe in, that there's two signals with different structures being added together. Okay, so once we've done that, then we just get similar effect. So adding in data here, instead of going exactly through the data, as we get more and more data, we get a tunnel of variance sigma squared. You can estimate what sigma squared is in this region here. And then we see points falling off the line. And that's typically the way we do regression, right? So the Gaussian process for regression with a smallish data set, that's exactly what we do. We have a covariance function plus a diagonal, because we're saying we've got additive noise. And additive noise is very easy to handle in the Gaussian process. So I hadn't thought about that data set, so I'll skip over that. So now, that does lead to a problem, because in many cases of machine learning, we're interested in cases where we've got non-Gaussian data. So we might want to build a classifier. So classifier is like binary data. So given these inputs, what is that output? Right? So given this digit, is it a 1, yes or no? So the yes or no is a binary output. So in that example, y would be either 1 or -1 or 1 or 0 or some encoding. So we've got some input image that comes through a function, and then we need to manipulate that function to give us the output image. Now this makes everything non-Gaussian. As soon as you introduce, so this is now a likelihood which is non-Gaussian. You relate your function to your observation. Here I've implied independently with this graph notation. You relate your function to your observation in a non-Gaussian way. All these Gaussian things fall apart, and you get a non-Gaussian entering in. And what we broadly do in Gaussian processes is we approximate. So in these examples, we have likelihoods which are non-Gaussian, P of yi given fi, and a general way of viewing all these approximations, I'm not going to go too in depth into each one, is to sort of assume that that's well approximated with something that looks like a Gaussian. So a typical likelihood, in fact, I've got that coming up, so I was going to draw up the board, but I think I've got it coming up. Once we've approximated that with a Gaussian, then we can do everything as a Gaussian process again. That's a very common approach. Another approach would be sampling. Sampling is typically, there are approaches to sampling that will give you near exact answers. They'll typically be quite slow. So we lose the benefit, or a lot of the benefit of being in Gaussian processes when we sample sometimes. But sometimes sampling is another approach. But let me give you a sort of idea of how we try and do that sort of approximation. So typically, we might have, so what I'm showing you now is some test prediction. Okay? So the test prediction is saying that currently it believes, given the training data, X and Y, so the training observations and the training inputs, matrix X, and a location where you're asking for a new prediction, we can make a prediction over F star. And it's a Gaussian prediction, assuming that this is a standard Gaussian model. So at the moment, we think it's negative. Now, the process of Bayesian inference is to combine that with a likelihood. So let's say we now make an observation of what the actual value of Y was for that input location X star. So this is a distribution over F star. This is not a distribution over F star. It's a function of F star, because it's the conditional distribution in our likelihood. It's a Gaussian likelihood of Y star given F star. So it looks like a distribution because Gaussians are very symmetric in their location parameter, which is F star, and their observation parameter, Y star. So this is now the likelihood. Now Bayesian inference says, surprising somehow I cut Bayes rule out of my slide. Bayes rule is, has anyone noticed that it's not really a rule, that it's just a consequence of product rule and sum rule? It's to make it sound more complicated than it is. In fact, Laplace never wrote it down and wasn't aware that Bayes had written it down. What makes Bayes' paper interesting is because Bayes actually speaks about the philosophical difference between treating a parameter as a variable. I won't go into that. But so Bayes' rule in this case is we've got P of Y star given F star. I'm going to leave off most of the conditioning. So this F star here has got a load of conditioning that I'm going to leave out. The product rule of the probability tells me that that's P of Y star comma F star. Yeah? And the product rule of probability also tells me that that's equal to P of F star given Y, P of Y. Yeah? So So that's just expressing the joint distribution. So complex Bayes rule says divide both sides by P of y. It's not very difficult, and I don't think it should even be given a name. It's a probability, right? It's saying that if I have these unknowns, then ignore that. The posterior distribution, what I expect F star to be, given the prior distribution and some relationship between F star and some new variable, is given by horror of horror, multiplying together those two distributions. So those two distributions are what I'm showing on the board. This is the prior distribution of what F star is. Okay, it's conditioned on previous data. But before I see that data, it's the prior. This is the likelihood given by my relationship between the data and F star. How do I get my updated distribution? I do this terrible operation of multiplying. And of course, I only have support in this sort of region here. If I multiplied, then I would get a distribution that was down here. P of y is the renormalization constant. It normalizes it for me. So the distribution has to be normalized, so you don't even need that bit. You can just say P of F star given y is proportional to P of y star given F star P of y star, like that. It's a multiplication operation that gives me the updated relief of what F star is. Now, normally in the Gaussian process, you're not going to do that operation explicitly. That's all embedded in the linear algebra I illustrated briefly before. I didn't derive it. But it's worth thinking about it a little bit for Bayes' rule in general, and then it's worth involving it for what happens if I've got a different type of likelihood. So this is the typical likelihood which we might use. I call it the Probit noise model. The Probit noise model predates the logit. Indeed, the logit is called the logit because the Probit was called the Probit, and they wanted to make it sound similar. But its form is this. So we have f coming in here from our Gaussian process, and we predict that y is 1 with a probability according to this function here. So if f is 0, the probability of y being 1 is given as 0.5. And if f is 4, it's approximately 1. And if f is minus 4, it's approximately 0. So we think of these as squashing functions, and they're widely used to get probabilities out of continuous variables. The probit itself is the integral over the Gaussian. It means things are a little bit more tractable. A common one to use is the logit or the sigmoid. But here's the probit. Sigmoid looks similar. Of course, the probability of being minus 1 is 1 minus that. So this is the sort of pictorial representation of our likelihood. So going back to our observation of what happens before, if we have a binary observation instead of a Gaussian observation, what we get in this space here, instead of that Gaussian thing here, we get a probit function. And now, the result of applying Bayes' rule is to take the product of this function and this distribution. So it's more obvious that this is not a distribution now, right? Before it could be a distribution. This is not a distribution in f star, it's a function of f star. And it's the squashing function. Or sometimes you think of it as the inverse link function as well. So now, when we do this operation here, what we get is something that's non-Gaussian. So this is like a squashed Gaussian, it's a rectified Gaussian. Now the reason we use the probit in this case is because it's, even though it's non-Gaussian, it's analytic. It's called a rectified Gaussian distribution, and it's a known distribution. But it's sort of squashed on this side. This side should be sticking out a little bit more, but it's being flat. Imagine if the probit was even tighter. Probit can go to be a step function, and then you get a totally rectified Gaussian as your posterior distribution. Here it's not fully rectified. It's partially rectified. Now what we do to deal with this non-Gaussianity is we then replace it with a Gaussian. So we then sort of ask ourselves the question, what Gaussian observation gets us closest to that rectified Gaussian? Closest. Now, the sense in which we mean closest gives us different types of approximation. So you can use something called the Laplace approximation, there's something called expectation propagation, there's something called variational methods. Each one of them has a different sense of what closeness is. And their quality varies according to what the likelihood is. They're going to be likelihood dependent. The expectation propagation approximation is a very good one for this type of noise. It works very well. So that's the sort of way in which we tend to approximate. Here's another example of a different type of likelihood. So here this is an ordinal categorical one. So there's three categories. So there's sort of small, medium, large. You know, we measure in coffee sizes in Starbucks. What's that? That would be large, larger, and really large. In America, you can't get anything, and now Britain as a consequence. There's nothing smaller than regular. So regular, large, massive. So some sort of categorical model that we're building things here. Now, in this case, you would combine one of these functions. And in fact, this function here in the ordered categorical model looks, broadly speaking, Gaussian. And indeed, if you increase the number of categories very, very large, this tends towards a Gaussian distribution. So if you've got ordered categories, so here's a nice example of it that actually has come up in an application. Let's say we're wandering around in this room, and I'm trying to tell where I am by measuring the strength of wireless access points, right? The signal strength I will measure is a function of my position in this room. So here I am standing here, and I'm far away from wherever the wireless access point is over there, so I measure that low, and I measure whatever the close by one here is high, right? Now these are, in theory, these are continuous measurements, right? So as I get here, this one will go up, 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 and up, and up, and that one will go down and down and down. In practice, no, because in practice devices, when that gets low enough, they'll drop the signal. So then you need something like a likelihood like this, where that says not reading that device. Not reading that device doesn't tell you how far away you are, it just tells you it's below a certain level. Also, as I get closer and closer to the device over here, the signal goes up and up and up, but then it saturates, right? As I get, it doesn't go infinite when I touch the device. It's saturated. So on the other end here, this is a good likelihood to use. For the levels in between, like signal strength 1 bar, 2 bar, 3 bar, 4 bars, then you want something like this. And in that region, a Gaussian approximation is fine. But actually, in these regions either side, a Gaussian approximation can give you a really misleading value. And indeed it does, if you try and navigate in that way. There's a couple of papers on that. So, let me just pause at that point. I'm not going to talk too much more about it. I mean, rather than giving you all the details of everything and lots of maths, I'm trying to give you the overview of the sort of problems that come up and how we deal with them in the current time. So I'm going to move on from non-Gaussian likelihoods, but it is a massive area and there's still people researching it. I mean, we do research on it to try and improve those approximations. But let me just pause and see if there's questions there.
It would be a very interesting, but if you have things like the Gaussian assumption for the non-Gaussian likelihood, can be okay if you have a Gaussian prior and then the non-Gaussian likelihood.
Yeah.
But in case if you have more data, your likelihood will dominate your prior. So your Gaussian approximation will get worse and worse with data.
Yeah, that's it's interesting that you mention it in that. I think yes, but I think not for the reason that you're driving at. The more data you get, the more your prior will always be exposed. That's a general thing. Like priors become less important when you've got very, very large data. But they also become, so they can become less important because you end up just fitting the data as long as you've got support. But what really worries me in the large data scenario is as you approach that zone, you'll be very badly calibrated. So here I sampled the data from the prior. So this is actually well calibrated. But this is the sort of situation as you've got increasing data, the support for your prior, the prior supports everything in theory, but how quickly it converges to that is one question. So here the priors collapse and have no uncertainty. That's really what gives me 9 points, that we're in that zone and that we've got a poor estimate of the uncertainty. But I think your question was more driving at the non-Gaussian assumption.
So you're not Gaussian, you're not non-Gaussian likelihood term dominates. Your posterior will be less and less Gaussian. So your approximation is worse in the large data, which seems counterintuitive.
Yeah, it actually doesn't work like that. Because, not that this is a particularly good thing, as you go larger and larger data, you get effects where your posterior distribution becomes a delta function. And as you get this, and I don't even know the proofs, but this is, the Laplace approximation is based around this. As you start getting close to that regime, you also become more Gaussian. So how does that come about? Well, I'm going to do a hand wave argument. You're sort of saying, okay, as I see more and more data, then I'm going to get more and more likelihood terms. Yeah, but then there's a large effect term. So in actuality, what tends, for this classification example, one way of thinking about it is in 2 dimensions, you get, this is something called version space, which probably no one's ever heard of anymore, W1, W2. So if we put a Gaussian prior over the weights of a logistic regression, so it's something like this. Now, what happens is, every time I see a data point, that data point is effectively a slicing through this space. So as data goes up and up and up, you're right, you get more and more data coming through. But actually what tends to happen is the posterior starts out being very non-Gaussian because it's a rectified Gaussian. But then over time, it actually collapses down to something very, very tight that it looks very Gaussian then. So part of me's like, well, I think the instinct for your question is right, but in Gaussians it's a special weird case where things go back to being Gaussian. But it's this regime where the posterior is very, very tight and it's a delta function, and it's a horrible regime to be in. Like, it means that your Bayesian equipment is non-functional, but the problem is you've installed the Bayesian equipment and you think it's functional, and you've got good, well-calibrated error bars, but you don't. So I mean, you're touching on all sorts of... So ironically, the opposite thing happens. I think your intuition's right, and if it weren't a Gaussian approximation case, I think it would perhaps be more right. But the opposite thing happens, it becomes more Gaussian, but it's still very worrying for different reasons. Sorry. Okay, other questions? Okay, so let me just finish today by talking about learning. So I've done very well. I've got this far through the lecture, and I've not shown you the formal Gaussian distribution until now. Okay, so this is what we're talking about, right? This is a Gaussian distribution, zero mean. You can put a mean in. You can have a mean function. You can have something that says, a priori I expect these functions to be centered around 1, or 7, or 3x. Or a neural network. You can put a neural network in here as your mean function, right? So the mean function is just itself a function of x. But everything works broadly the same, and it clutters up the notation, so we're going to leave the function out, the mean function out for a moment. So this is what we're talking about. We're talking about a Gaussian density where this is the covariance function, this is our data, and the input data is embedded in k. So for a finite training data set, k is n by n, and it's a function of x, our training data. And y is an n-dimensional vector of all our training outputs. Now notice one thing. This is not independent. It's most likelihoods you write down over a data set start with a big old product sign. So the first thing most people see when they write down the likelihood over their data, and indeed our internal likelihood, given some parameters theta. Well, let's make it look like a linear regression. Independence, right? It's an IID assumption. I think it's one of the most damaging things that we write down when we model, because it's totally nonsensical when people say, my model's IID. Why is it nonsensical? What are we saying when we say this? What we're saying is that there's an independence between y1 and y2. So if y1 and y2 are independent, then how will we be able to predict anything about y2 given y1? What's the answer to that question? Why is that possible? They're coming from the same distribution, but they could be coming from, like, so if I sample, I'm God, I'm creating. I sample your height from a Gaussian distribution, with a mean of 1.7 and some variance. And then I sample your height. So they're coming from the same distribution. But I can't now predict anything about your height, given your height, apart from what the average heights will be. But I don't gain any extra information. But there is something in there, the mean, right? So we're conditioning on the parameters. So they're coming from the same distribution, conditioned on those parameters, they're independent. Right? And I think when we say IID, we keep forgetting about that. When we say IID, we're saying that epsilon, the residual I talked about earlier, is IID. Sorry, the vector of epsilon is IID. Yeah, we're saying nothing probabilistic about them. So when we say IID, we're going all the way back to that first class model. Any actual model where you deal with uncertainty in the parameters will always not be IID. It is defining, this model is defining correlations between your data. Right? And that seems to be, if you're being probabilistic about modeling, that's what you should be thinking about. Defining the relationships between your data. That's what graphical models do as well. Graphical models do it by assuming conditional independencies. So there's two ways you can tractably do this effectively. I think, or tractably easily. One is to assume conditional independence between your data, right? And that's what a graphical model will do. And then you get this sparsity structure in the graph. And another one is to assume that there's only second order effects. So if you assume the second order effects, then you get covariance, right? Now, we've assumed the second order effects and nothing beyond that, because that's what a Gaussian says. But unfortunately, if we try and go beyond that, we get tractability problems. Okay, so this is the form of the likelihood. Now, what I want to show you is that actually, we can find the parameters, the alpha and the L, of this likelihood by just doing standard maximum likelihood. Because people, when they deal with these kernels, okay, where does alpha and L, the length scale and the overall scale, and the noise come from? So what we do is we always look at log likelihoods. So I want to just look at the log likelihood here and sort of point out that this model is made up of a log determinant and this thing here, which is a quadratic form. And they're both dependent on the form of the covariance matrix. So I always think whenever you do optimization, you should minimize, because mathematicians are pessimists, and that's what they decided early on, not maximize. So we look at the negative log likelihood, and we write that down as an objective function, right? We're minimizing the negative log likelihood. So that has the same two terms, but just with the sign change. So we're trying to minimize here. Now, before I talk in detail about that, I want to look at that decomposition of the covariance we talked about earlier, which is the eigenvalue decomposition of the covariance. So that's what PCA was. The PCA is a little bit more than that. PCA is actually a Gaussian model, where you look for the principal axes. So this is a covariance matrix like I did before. The eigenvalue decomposition of the covariance matrix says that you can represent any covariance matrix by a principal axes, which are represented by a diagonal matrix lambda, so the length of each axis, and a rotation permutation matrix, which moves those axes around. So the way I get this covariance matrix is I start with a sort of a standard axis, I scale one of them up, and then I rotate everything around. And that's one way of thinking about how a covariance function can come about, and it's that decomposition you're doing in PCA on the sum of covariance. So that's one way of looking at it, and I like that way of looking at it because it allows us to look at these two terms a little bit better. So there's two terms, and this term here turns out to be responsible in, we're not doing optimization, we are doing optimization, but philosophically we're not approaching it from an optimization perspective, but it's an optimization of problem. And an optimization perspective would look at this and say, well, there's two terms, there's a data fit term and a regularization term. The data only appears here, so this has to be the data fit term. So if there's any regularization, it's going to be in here. So that is the log determinant, which some people might recognize as the entropy. But let's talk about it in a moment. So the capacity control, if we look at lambda, that basis function there, it's giving us a sort of the axis of a box. Now the determinant of k is actually, because it's just a rotation matrix either side, the determinant of k is just the determinant of lambda. The determinant of lambda is just the product of these diagonal values. So these diagonal values give us a box like that. Now going back to look at this form here, there was a lambda squared in here. We'll come back to that. So the square root of this matrix is lambda times r, right? And that's what I'm showing you here, lambda rotated. That's like visualization of the square root of this matrix on its principal axis. So that is representing a little box. And of course, if we go to a third dimension, it represents a cube. So the determinant of lambda is representing a volume or a hypervolume. I actually didn't study linear algebra at university because I did mechanical engineering. So I don't know how many people are aware that determinants are representing volumes? 3 or 4, yeah. So it's good to know. It's a really important aspect to know. Of course, if we rotate that, so if we apply r to it, the volume doesn't change, and actually the determinant doesn't change. That's one instinctual reason why the determinant is not affected by a rotation, because volumes don't change under rotation, right? So that's giving us the square root of the covariance, the determinant of the covariance. But if you look back here, half up to there. So what you are computing here is the log of the square root of the volume of K. Right? That makes sense. It's the normalizer of the Gaussian. It's the footprint of the Gaussian. It's the amount of space the Gaussian is taking up. It's the number of different functions that Gaussian process can represent. Is the determinant of that covariance there. So it's a capacity term. Of course, in the end, you don't do it on this square root here, because in theory, the thing I didn't point out is any one of these lambdas could be negative, and therefore this thing would be negative. So instead of looking at this, you look at the square of it to make sure they're all positive, and then square root with that half, effectively. All you're doing is looking at the log volume of the process, which is actually also the entropy of the Gaussian process. Now, the data fit term is different. The data fit term is centered on 0. If I plot the data fit, the contours of this term, as a function of y1 and y2, I get a quadratic well. I've used 2 contours to show a quadratic well, to show it's not a Gaussian. I use 1 contour for a Gaussian. This is a quadratic well. So here's the bottom, which is 0. If both y's are all 0, then we'd be at 0 here. But then as we increase, according to the principal axes, as we increase here, we'll go up the well. So it's easier to leave the well in this direction than it is to leave the well in that direction. So what that means is, if we have a data point here, what is the process looking to do? It is saying y1 and y2 are close together. They're similar values. So how can it deal with that? It can do 2 things. It can expand this up. Right? Expanding this up is equivalent to changing alpha. So changing alpha would allow you to expand. If I make alpha very large, then in the inverse covariance, alpha will be very small, and this whole thing will go down to 0. So expanding this up is one way of dealing with that. But expanding that up will increase the determinant term. It increases the capacity of the model. So another really clever way, it can't do this move precisely, move I'm about to show you, but what if it just rotates? Okay? So if it rotates, if it says, therefore there's correlation, how can it rotate? It can't rotate. It's not free to do anything because it's a parameterized covariance. But if y1 and y2 are close together on the input, it can set the length scale such that they become correlated. And a rotation move of that effect, if it were able to do it, wouldn't have an effect on the determinant. So you get these capabilities to improve the data fit without covering a very large number of functions. And I'm just sort of using that to illustrate the way in which the model's regularized. So just as a final thing, because I'm slightly over time, if we look at the fit to a data set here, now first of all, this is the mean function, and then this is the marginal variance. Everyone would start saying, oh, that's overfit, it's overfit, you've overfit, you've overfit. No, that's rubbish. It's such a silly term. You haven't overfit because the mean function looks like it's overfitted, but the prediction is not the mean function. The prediction is all functions that go through this. And all those functions will be going up and down madly. They will go through these points. I mean, in some sense, I would rather say it's an underfit. It doesn't know what's going on, right? It is going down to 0. And here it's saying, I haven't got a clue. No idea. So is that an overfit? I don't think so. It would certainly be an overfit if this was an SVM. But the concept is different, because as we move away here, it's saying no idea, right? It's returning to the prior because the length scale is small. Now what I'm going to show you is trying to fit to this data, just changing the length scale. I've set correctly the other parameters, so they've got the other correct fits. As I change the length scale, I'm showing visualizations of the log capacity term and the data fit term. And of course what happens is my data fit gets worse as I increase the length scale, which is why people think of it as overfitting. But my capacity term is getting better. So the capacity term as I'm increasing the length scale is dropping down and the data fit's getting worse. And the sum of these two is the purple. So the fact that the capacity term is dropping down means it's dominating until this point where now the poor quality of the data fit dominates. So you get a minima, which in this case is around 1, which is actually the length scale I use to generate the data. Of course, it's not going to be exactly 1 because it's a continuous space. You get a minima that suggests what the fit should be. So when you're doing maximum likelihood in the Gaussian process, that's why it's choosing. So actually, there's not much to choose between those two, according to the model. And that's where you have to start doing sampling over the parameters of the covariance function as well. But you gain the ability to estimate the parameters of the covariance function. This puts you in a very different ball game to standard kernel methods. So in standard kernel methods, people typically choose the parameters by cross-validation or some other technique like that, and that limits you to very few parameters. Because we're doing maximum likelihood here, we sometimes do Gaussian process covariance functions with very many parameters. It leads to its own problems, like it's like trying to fit a highly parameterized model, and you have to deal with those, but it's the sort of thing you can do. Now, I've got another thing. I'm going to start again tomorrow on that example I spoke about, which illustrates how you can use this to get publications already. That's from a few years ago now, 2011. But I'll start on that this afternoon, and I'll just pause there to go over on site. You can stop there and check very, very quick questions. We took questions as we went along, but I wanted to finish successfully. Everyone's hungry. Okay, well, we can start to take questions at the beginning of the next session as well, because I'm 4 minutes over. So we'll stop there. And, what do they do now?
Have a lunch.
Have a nice lunch.